Hello students, welcome to lecture 12 MVUE through Sufficient Statistic, Minimum Variance Unbiased Estimator through Sufficient Statistic. We saw that MVUE is the most desirable estimator. Kumar-Rao theorem sets a bound on the minimum variance of the unbiased estimator. If the MVUE reaches the CRLB, it can be obtained through the factorization of this matrix, log likelihood matrix, del L del theta matrix, that is equal to I theta into theta hat minus theta, where theta is the parameter vector, theta hat is the unbiased estimator vector, and I theta is the Fisher information statistic. However, the CRLB may not be achieved by the MVUE. So, in that situation, the concepts of sufficient statistic and complete statistic may be used to find the MVUE under certain conditions. So, we will introduce the concepts of sufficient statistic and complete statistic in this lecture. We will start with sufficient statistic. The observation x1, x2 up to xn contain information about the unknown parameter theta. So, because of that, we will be able to estimate theta from the observations. An estimator should carry the same information about theta as the observed data. Whatever information is there for theta, same should be carried by the estimator also. Now, we will go to sufficient statistic. A statistics T x1, x2 up to xn of theta is called sufficient if it contains the same information about theta as contained in the random samples x1, x2 up to xn. In other words, the conditional PDF f x1, x2 up to xn as a function of theta given t is equal to t does not involve theta. So, this conditional PDF does not involve theta, then we will say that this statistic t x1, x2 up to xn is sufficient. Now, in the case of discrete random variables x1, x2 up to xn, the conditional PDF above is replaced by the conditional PMF. So, that means in the case of discrete random variable x1, x2 up to xn, the statistic t x1, x2 up to xn of theta is sufficient if this conditional PMF of the data given t is equal to small t does not involve the parameter theta. So, we have defined the sufficient statistic, and let us see an example. Suppose xi is normally distributed with mean mu and variance 1 for I is equal to 1 to 2, and t x1 x2 is equal to x1 plus x2. We will examine if t x1 x2 is a sufficient statistics. Now, the conditional PDF f x1 x2 as a function of mu given t x1 x2 is equal to small x1 plus x2 is equal to, that is the joint PDF f x1 x2 x1 plus x2 as a function of mu divided by the marginal PDF, that is f x1 plus x2 as a function of mu. So, this is the conditional PDF in terms of the joint PDF and marginal PDF. Now, the same can be written as f x1 x2 mu as a function of mu divided by f x1 plus x2 as a function of mu, because x1 x2 and this x1 plus x2 is a function of mu. Therefore, the PDF will be same as the PDF of x1 x2. So, that way this expression is equal to joint PDF of x1, x2 as a function of mu divided by PDF of x1 plus x2 as a function of mu. Now, since xi's are IID Gaussian, therefore, joint PDF will be the product of the individual PDF. So, that way f of x1 into f of x2 we can write like this. So, 1 by 2 pi into e to the power minus half x1 minus mu whole square plus x2 minus mu whole square. So, this is the joint PDF divided by marginal PDF, that is the PDF of x1 plus x2. Now, I know that x1 is normally distributed with mean, mu and variance 1, and x2 is also normally distributed with mean, mu and variance 1. Therefore, x1 plus x2 will be distributed as normal. Mean will be mean of x1 plus mean of x2, that is 2 mu, and variance of x1 plus variance of x2, that will be is equal to 2. So, that way this will be normal with mean 2 mu and variance 2. So, therefore, this marginal PDF of x1 plus x2 will be given by this. Now, if we simplify, we will get this expression. So, 1 by root pi will be only there, and bringing this to the numerator we will get like this. And ultimately, if we simplify this expression, we will get the same equal to 1 by root pi into e to the power minus 1/4 into x1 square plus x2 square plus 2 x1 x2. So, here we see that mu is not involved. So, this conditional PDF does not involve mu. Therefore, this statistics x1 plus x2 is a sufficient statistic. So, we see that this conditional PDF does not involve any parameter mu, hence T x1 x2 is equal to x1 plus x2 is a sufficient statistics for mu. We will see one example for a statistic which is not sufficient. Suppose we have this T x1 x2 is equal to x1 plus 2 x2. Earlier we considered x1 plus x2, now x1 plus 2 x2. Now, this conditional PDF f x1 x2 as a function of mu, given that T x1 x2 is equal to small x1 plus 2 x2, that we can write as joint PDF of x1 x2 as a function of mu divided by marginal PDF at point x1 plus 2 x2 as a function of mu. So, if we write the Gaussian PDF for these two, then we will get numerator as this and denominator as this. Here we see that from these two expressions we cannot cancel out mu, therefore, this will involve mu. So, therefore, this conditional PDF given this statistic is will involve mu, therefore, it is not a sufficient statistic. And now, we will discuss one important theorem, what is known as the factorization theorem, that is Neyman and Fisher factorization theorem. This is one of the ways to determine whether a statistic is sufficient or not. For continuous random variables x1, x2 up to xn, this statistic T x1, x2 up to xn is a sufficient statistic for theta if and only if this joint PDF as a function of theta is product of two functions g and h. G is a function of the parameter theta and the statistics Tx, and h is a function of data only, it is a function of x, h x1 x2 up to xn, it does not involve any theta. So, that way we factorize the joint PDF in terms of two factor, where g theta Tx is a non constant, it should be a proper function of x1, x2 etc., and non-negative function of theta n t x1, x2 up to xn, and hx, hx1, x2 up to xn is a non-negative function of x1, x2 up to xn, and it does not involve any parameter theta. So, then we say that this statistic will be sufficient. So, that way we have to see the joint PDF. If it is a product of two factors, one factor involves theta and t, other factor is a function of hx only, then this statistic will be sufficient. For discrete case, we will be considering the condition in terms of joint PMF. Therefore, Tx is sufficient if and only if this joint PMF Px theta as a function of theta is product of g theta Tx into Hx, where g and h are defined as earlier. So, we have introduced the factorization theorem. We will try to prove this considering the discrete random variables x1, x2 up to xn. Let us denote the particular value of Tx by small t, that is small t is equal to t of small x1, small x2 up to small xn. Suppose Tx is sufficient statistic, then PMF, probability mass function of x as a function of theta, that is equal to probability of x is equal to x as a function of theta. Now, if we introduce any function Tx, then this joint probability will be also same. Therefore, this probability is same as probability of x is equal to small x and Tx is equal to t as a function of theta. Now, this I can write as probability of Tx is equal to t, of course, as a function of theta, and then into conditional probability, probability of x is equal to small x given that Tx is equal to t, and this will also be a function of theta. So, this is by applying the conditional probability result. Now, I know that Tx is a sufficient statistics. Therefore, this factor will not involve any theta. So, I can write this term simply as probability of x is equal to small x given that Tx is equal to t, because it does not involve theta as Tx is a sufficient statistic. So, this term now I can expand in terms of the joint PMF, summation of joint PMF for those value of x for which Tx is equal to t. Into this part, now this is a function which does not involve any parameter or the statistics, it is simply a function of x. So, that way we have established that this joint PMF is product of g and h, where g is a function of theta and Tx and h is a function of x only, and it is given by this probability of x is equal to small x given that Tx is equal to t. So, we have proved this part, and now let us see the converse part. Suppose Px is equal to g of theta Tx into Hx. This is true. Then we have to show that Tx is a sufficient statistic. Now, this conditional PMF, probability that x is equal to small x given that Tx is equal to t as a function of theta. Now, you apply the definition of conditional probability, that is probability of x is equal to small x, and this comma is for n, Tx is equal to t as a function of theta, divided by the marginal probability, probability that Tx is equal to t as a function of theta. Now, since Tx is a function of x, this we can write as probability of x is equal to small x theta divided by probability of Tx equal to t as a function of theta. Now, we will apply this factorization result. So, we will get g of theta t into Hx divided by summation g of theta t into Hx x such that Tx is equal to T. So, this g of theta t will be common for all. So, we are taking common here, and therefore, this denominator will be g of theta t into summation h x x such that Tx is equal to T. So, this g of theta t and this g of theta t will get cancelled. Therefore, it will be simply h x divided by summation h x x such that Tx is equal to T. And clearly, this expression, that is this conditional PMF, does not involve any parameter theta. Therefore, Tx is a sufficient statistic. Therefore, we have proved both necessary and sufficient conditions. So, for discrete case, Tx is sufficient if and only if this joint PMF is a product of two functions g and h. And similarly, for the continuous case also we can establish that Tx is sufficient if and only if the joint PDF is product of two factors. One is function of theta and Tx, other is simply a function of x. We will consider an example. Suppose x1, x2 up to xn are IIT Gaussian random variables with unknown mean mu and known variance 1. Then Tx is equal to summation xi I going from 1 to n is a sufficient statistic for mu, because we will write this now joint PDF as a function of mu. This is product of the individual PDF, marginal PDFs, and all are IID. So, same mean and same variance 1, and this product we are writing as summation, and this now we can expand xi minus mu whole square. So, that we will get two factors here now. One factor is this and the other factor is this. We observe that this second factor, this is a function of xi only, and the first factor is function of both the statistic and mu. Therefore, we conclude that Tx is equal to summation xi I going from 1 to n is a sufficient statistic for mu. So, through factorization theorem, because this joint PDF is factorized into two terms, one term involves xi only, other term involves the statistic and the parameter. Now, we will establish one very important theorem, Rao Blackwell Theorem. Suppose theta hat dash is an unbiased estimator of theta and Tx is a sufficient statistic for theta. Then another estimator we will get theta hat, that is the conditional expectation of theta hat dash given Tx. This is the conditional expectation. This is unbiased, not only unbiased, but its variance of theta hat is less than or equal to the variance of theta hat dash. So, this is the Rao Blackwell theorem corresponding to any unbiased estimator theta hat dash. We have another unbiased estimator with lower or equal variance. We will prove this. E of theta hat will be E of, because theta hat is equal to this, E of theta hat dash given Tx. Now, using the property of conditional expectation, so we have a property like E of x given y. So, this will be same as E of x. So, this conditional expectation, which is a random variable in terms of y, and if we take the conditional expectation in terms of y, then we will get E of x. Now, we apply the property of conditional expectation. E of theta hat is equal to the expectation of this conditional expectation, E of theta hat dash given Tx, and this will be same as E of theta hat dash. And this is unbiased, therefore, it will be equal to theta. Therefore, E of theta hat is equal to theta. Therefore, theta hat is an unbiased estimator of theta. So, we got the unbiased property of theta hat. Now, let us see the variance of theta hat dash. By definition, it is equal to E of theta hat dash minus theta whole square, because it is an unbiased estimator. Now, apply this conditional expectation property, that will be E of theta hat dash minus theta whole square given Tx. Now, this mean square value theta hat dash minus theta whole square is greater than equal to the square of the mean. So, that way we can write in terms of square of the mean here. So, now E of theta hat dash given Tx, that will be equal to theta hat, and this is a constant quantity. So, E of theta given Tx will be theta itself. This quantity will be equal to E of theta hat minus theta whole square. Therefore, variance of theta hat dash is greater than equal to variance of theta dash. That means variance of theta dash is less than or equal to variance of theta hat dash, that we established. Thus, this sufficient statistic Tx help us to find a better estimator theta hat is equal to E of theta hat dash given Tx, and variance of that estimator theta hat is less than or equal to variance of theta hat dash. But still we have the question, is theta hat that is equal to E of theta hat dash given Tx is a minimum variance unbiased estimator. To answer this question, we have to discuss one more concept, that is the complete statistic. Complete statistic. A statistic Tx is said to be complete if for any theta and a bounded function g of Tx, the condition E of g Tx is equal to 0 for all theta implies that probability of g Tx is equal to 0 is equal to 1. That means g Tx will be 0 with probability 1. It also means that there is no non-zero unbiased estimator for 0. Suppose 0 is the quantity and we want to find out any estimator for 0 such that E of gtx is equal to 0. This is the definition for unbiased estimator, but then this gtx must be equal to 0 and there is no non-zero unbiased estimator for 0. That way also we can interpret. And completeness is a property of the distribution of Tx. Same estimator Tx may be complete for one distribution, but may not be complete for another distribution. We will give one example. Suppose xi is our IID Bernoulli random variable. This is the symbol for Bernoulli random variable. It is symbol is like binomial with n is equal to 1. That is why we are writing p1 theta. And parameter theta is the probability parameter, and Tx is equal to summation xi I is equal to 1 to n. Clearly, Tx is a binomial distribution with parameter n is the number of repetition and theta is the success parameter, because Tx is a sum of individual Bernoulli random variables. So, it is a binomial with parameter n and theta, and Tx takes value success may be 0, 1 up to n. Thus, the probability mass function of at point t will be given by nct theta to the power t into 1 minus theta to the power n minus t, t going from 0 to n. And expected value of gtx, tx is a function of x now. So, if I consider expected value of any bounded function gtx, it will be given by this summation t going from 0 to n gt into n ct into theta to the power t into 1 minus theta to the power n minus t. Now, we will apply the condition for completeness. So, E of gtx will be this summation as I showed earlier. Now, 1 minus theta to the power n is common, so that I can take out. So, it will be same as 1 minus theta to the power n summation t going from 0 to n gt into n ct into theta by 1 minus theta to the power t is equal to 0. So, this equality can be written as this for all theta in the open interval 0 to 1. So, theta can be anything between 0 and 1 excepting 0 and 1. Therefore, we get now one condition, this part we can cancel out, summation t going from 0 to n gt into n ct into theta by 1 minus theta to the power t is equal to 0. Now, this condition will be satisfied because it is a polynomial in theta by 1 minus theta. So, this polynomial can be 0 if and only if all coefficients vanished, that means gt must be equal to 0 for t is equal to 0, 1, 2 up to n. Hence, t is a complete statistic. So, in this case we proved that t is a complete statistic. Now, we will consider another example. Suppose x1, x2 up to xn are IID, normal, 0 mean, variance sigma square random variables. They are normally distributed with mean 0 and variance sigma square, and Tx is equal to summation xi I going from 1 to n. Clearly, because it is a sum and all xi are 0 mean, Tx will be normal distribution and with mean 0 and variance n sigma square, and we observe that E of Tx is equal to 0. So, this is for non-trivial x. Therefore, if we consider the equation E of g Tx is equal to 0, it will have non-trivial solution g Tx is equal to Tx. If we substitute g of Tx is equal to Tx, then this equation will be satisfied. Therefore, Tx, that is equal to summation xi I going from 1 to n, is not a complete statistic in this case. Let us summarize the class. A statistics T x1, x2 up to xn of theta is called sufficient if the conditional PDF, that is conditional PDF of x1, x2 up to xn as a function of theta, given that t is equal to t, or the conditional PMF p x1, x2 up to xn as a function of theta, given t is equal to t, does not involve parameter theta. Conditional PDF or conditional PMF does not involve the parameter theta. Then we discussed the factorization theorem. For continuous random variables x1, x2 up to xn, this statistic Tx1, x2 up to xn is a sufficient statistic for theta if and only if we can factorize the joint PDF as a two factors. One factor g is a function of theta Tx and other one is hx, which is simply a function of x1, x2 up to xn. For discrete case, Tx is sufficient statistic if and only if joint PMF is product of these two factors. Now, Rao Blackwell Theorem. Given an unbiased estimator theta hat dash, the sufficient statistic Tx helps us to find a better estimator. Theta hat is equal to E of theta hat dash given Tx. This is the conditional expectation of theta hat dash given Tx. Now, this estimator has the property that it is not only unbiased, but its variance is lower than or equal to the variance of theta hat dash. Then we discuss about complete statistic. A statistic Tx is said to be complete if for any theta and a bounded function g of Tx, the condition E of g Tx equal to 0 for all theta implies that g Tx is equal to 0 with probability 1. So, this is the definition of complete statistic. Now, we will look into the MVUE in terms of a complete sufficient statistic in the next lecture. Thank you.